So, today's class we'll be discussing mainly about electromagnetic radiation. So, does anybody know how radiation is generated? So, yes? No, not exactly that. The radiation occurs when you have a charge in acceleration. Okay. So, previously, you know that moving charge produces current, and the current gives rise to a magnetic field, right? So, if you're okay, I will upload the link immediately. Yeah. Okay, so the thing is that if I have a charge moving with a constant velocity, then it will give rise to a constant current, and that constant current will give me a constant magnetic field, right? So now if I have an accelerated charge, then the velocity of the charge changes with time. So in that case, the current will change with time, and the magnetic field generated because of this charge, that will also change with time, right? And as per Faraday's law, we know that del B del T is equal to minus of curl of E. So a time varying magnetic field will give rise to an electric field, which will also vary with time. And so this coupled electric and magnetic field ends up giving rise to electromagnetic radiation, right? So because for any propagating wave, you need to have an electric and a magnetic field which oscillates with time, right? So in this way, an accelerated charge can give rise to radiation of different sorts. So in today's class, I'll be discussing a few problems related to electromagnetic radiation. Okay, this session has not been uploaded yet. I will upload it after I am done with the session. I'll save the recording and then upload the session. Okay. Okay. So can you all see my screen now? Okay. Okay. No. Okay. So the first question says, if there is an antenna located in a city, is a source of radio waves. Okay, the antenna is a source of radio waves. So what is the time it takes for a wave to reach a town 12,000 kilometer away from the antenna? Okay, so this is the distance of the town from the antenna, and as you know, EM wave propagates in air with almost the speed of light. So that is why the answer is simply distance, which is 12,000 kilometers divided by the speed of light c, which is the time taken for the electromagnetic wave to propagate from the antenna to the town. So this will be the answer, 40 milliseconds. And in the second question, this asks, what is the radiation resistance of a half wave dipole in ohm? So this has been stated in many engineering books. So the radiation resistance of a half wave dipole is given by 73 ohms approximately. And in question 3, which of the following three ones tells that we have a normal dispersion region? So which of the following is true in a normal dispersion region? So the correct option here will be option A, that is d omega by d beta is greater than 0. Why? Because beta is basically 2 pi by lambda, where lambda is the wavelength. So beta is my wave number. So d omega by d beta actually gives me my group velocity. And in a normal dispersion region, group velocity is greater than 0. If there is anomalous dispersion, then it is less than 0. So here the correct option is option A, that is d omega by d beta is greater than 0. In question number 4, a very small thin wire of length lambda by 100, where lambda is the wavelength, has a resistance, has the radiation resistance of what? So the case given here is that of a very small thin wire, and for this wire the formula for radiation resistance is basically this. So the radiation resistance of a short thin wire is 80 pi square into L by lambda whole square, where L is the length of the wire. Okay, so if I put L equal to lambda by 100, then I can calculate my final answer, which is 0.07 ohm. Alright. Now in question 5, it asks what is the directivity of a half-wave dipole. So the directivity of a half-wave dipole is 2.15 decibels. Okay. Any doubts or questions till now? Okay. Okay, then going on to question 6. A magnetic field of strength 5 microampere per meter is required at a point on the theta equal to 2, that is theta equal to pi by 2 region, at a distance of 2 kilometers from an antenna in air. Now, on neglecting ohmic laws, what is the power transmitted by the Hertzian dipole antenna of length lambda by 25? So I have a Hertzian dipole antenna whose length is lambda by 25, and it transmits power. And what is it is required that at 2 kilometers from this antenna I should get a magnetic field whose strength will be 5 microampere per meter at an angle of theta equal to pi by 2 with respect to this antenna, right? So what should be the strength of what should be the power radiated by this antenna? So the formula for a magnetic field due to a Hertzian dipole at a distance d from it at an angle theta is given by this: I0 into beta dl sine theta by 4 pi d, where beta is 2 pi by lambda. Dl is the length of the dipole, which here length of the antenna, which is lambda by 25. Theta is the angle of the position of where we have to calculate the magnetic field with respect to the antenna. Here theta is pi by 2, and d is the distance of the position from the antenna. Okay, so I have all my values known over here. If I put this in, I can calculate h in terms of I0, and h is already given to me as 5 microampere per meter. So then substituting these values, I obtain I0 equal to 0.5 ampere. So this is the current which should be passed through my antenna in order to generate a magnetic field of 5 microampere per meter. Okay, now the power transmitted by the antenna would be I0 square into radiation resistance, where I0 have already obtained, and radiation resistance for a Hertzian dipole is given by this formula: 40 pi square into dl by lambda whole square, where dl is the length of the antenna. So if I substitute these values, then I can calculate the power transmitted like this. Okay. So in question 7, what is the transmitted power in case of a half-wave dipole? So previously we had a Hertzian dipole, now we have a half-wave dipole. So the procedure is similar, only difference is that the formulas will be different. So for a half-wave dipole, the magnetic field is given by this formula: I0 into cos of pi by 2 cos theta divided by 2 pi d into sine theta. So since theta is equal to pi by 2, this quantity becomes 0, and so cos of 0 is equal to 1. So h becomes equal to I0 by 2 pi d. So again, on substituting the values of h and d, I can calculate I0 equal to 20 pi milliamperes. Now the power radiated by this half-wave dipole, this is given by I0 square into radiation resistance, and radiation resistance for a half-wave dipole is 73.1 ohms, as we had seen before. So the radiated power is 144 milliwatts. Okay. So in question number 8, the electric field intensity at a distance of 10 kilometers from an antenna having a directive gain of 5 decibels and radiating a total power of 20 kilowatts is what? Okay, so this is a new quantity given here, that is a directive gain. So how do we calculate the electric field in this case? So since the directive gain is given as 5 decibels, that means GD, which is my directive 5 decibels, is basically 10 into log 10 times GD. So GD becomes equal to 3.162. So this is my directive gain. Okay. Now this is the total radiated power by the antenna, 20 kilowatts at a distance of 10 kilometers. So then the average power which is radiated by the antenna would be the gain into total power by the surface area of the sphere at a distance having a radius of d. Okay, so this is GD into total power divided by 4 pi d square. And we had seen earlier that the power transmitted by an electromagnetic wave is given by this formula, mod Es square by 2 eta, where Es is the amplitude of the electric field associated with the electromagnetic wave, and eta is square root of mu naught by epsilon naught. Okay, so if I substitute these values here, then I can calculate Es in terms of my already known quantities. And so putting in the values of eta, GD, radiated power, and D, I can calculate electric field from this formula. So then Es turns out to be equal to this. So any doubts or questions till now? Or shall I move on to the next one? Okay. So if there are no doubts, then all right. Okay. So in question 9, the maximum effective area of a lambda by 2 dipole operating at 30 megahertz is what? So for this we need to use the formula of the effective area of a lambda by 2 dipole, that is a half wave dipole. So the effective area is given by this formula, lambda square by 4 pi into the directive gain. Now the directive gain in general can be a function of the angles theta and phi. Okay, so it depends on which position of the sphere you are. And it's given to me that the frequency of operation of the antenna is 30 megahertz. So then the wavelength at which the electromagnetic wave propagates, that is equal to c by f, which is 10 meters. Right. Now this directive gain GD can be written in terms of this formula, which is eta by pi into radiation resistance into some function f square of theta. And since I already know the radiation resistance for a half wave dipole and I know the value of eta, I can calculate this quantity. So this becomes equal to 1.64 into f square of theta. Now this function, it has a maximum value of 1 at some value of theta. So in this case, the maximum value of GD would occur when this function is equal to 1. So that is why the maximum of GD is equal to 1.64. Right. And once I get the maximum of GD, I can actually calculate the maximum of the effective area, that is AC. So simply substituting this value, I get the maximum effective area is lambda square by 4 pi into 1.64, which is this value. So this one's clear, right? Okay. Okay. So then we have the last question, that is question 10, which tells me that the transmitting and receiving antennas are separated by a distance of 200 lambda and have directive gains of 25 and 18 decibels respectively. If 5 milliwatts of power is to be received, then what is the minimum power that is transmitted? Okay. So this is the distance between the receiving and the transmitting antenna, which is 200 lambda. So GT is the directive gain of the transmitting antenna, which is equal to 316.23, and GR over here, this is the directive gain of the receiving antenna, which is 63.1, and PR is the power which is being received by the receiving antenna, which is 5 milliwatts. So then by using this Friis equation, one can calculate the power which is being transmitted. Okay, so the receiving power is equal to gr into gt into lambda by 4 pi d whole square into pt. Okay, so from this we can calculate pt, which is the power that is being transmitted. So since I already know the values of d in terms of lambda and the receiving power and the two directive gains, I can calculate pt using this formula, which turns out to be equal to 1.583. All right, so yeah, those were the questions which I had to discuss today. So are there any doubts or anything you want to ask? Yes. Okay. Exam they usually allow calculator, I think. Hmm. NPTEL exam or college exam you're asking? Oh, NPTEL exam I don't know, but college exams they allow. Right, right. So I think you might have an online calculator of some sorts, like they have in the competitive exams. No, I mean online calculator meaning that like you'll be typing the answers down on their web page. So over there you might be having some sort of a calculator and things like that. I'm not sure about this. Oh, okay, okay. No, no, that was 6 to 7. Okay, okay. No, no problem. The recording I uploaded to YouTube yesterday or day before yesterday, I think. So, yeah. Okay, yeah.